So the first paper in the first session is on mean estimation for general norms with statistical queries, and Eric Weingarten will be giving the talk.
Okay, thank you. Okay, good. So this is joint work with Jerry Lee, Alexander Nikolov, who's right there, and Ilya Rajenstein. Okay, so let me first set up the problem as well as the context. So we'll work in the statistical query model, and this was introduced by Kearns in '93. So the main setup is that we have a player, and she gets sample access to some unknown distribution D on some particular domain, and we want to learn some information about the distribution. So in general, we think of these algorithms working by you take some random samples, and then you do some computation and output something. And now Kearns in '93, what he suggested is that we should restrict the class of algorithms which we focus on to these called like statistical query algorithms. And the high-level idea is that we want our algorithms to take into account like these high-level trends, these statistical properties of the distribution, rather than the nuances of particular samples. And the way this is formalized is saying that rather than the algorithm observing samples, what we'll want is that at each point, our player gets to make statistical queries, and all this is a function g, which maps the elements of the domain to -1, 1. So these are some any arbitrary map, as well as this error parameter tau. And upon making this query, what the player observes is an estimate to the function under the distribution, the unknown distribution. So the algorithm proceeds in these rounds, making these queries, receiving this error up to error parameter tau, and finally outputs some answer. Good. And we'll measure the complexity of these algorithms by the number of queries that the algorithm makes and the error parameter tau. So in particular, we want the number of queries to be as small as possible while supporting error which is as large as possible. Okay. Good. So recently, there's been this work in trying to use a statistical query model in order to show hardness for certain computational problems. So this was done by Feldman, Grigorescu, Raisin, Vimpal, and Zhao. And what they were doing, basically, if you can cast your computational problem as a learning from a fixed set of samples from a particular distribution, then you could hope to get some hardness results by showing that your algorithm can't work in the SQ model. So this basically suggests that all these problems, or these algorithmic approaches, which we know how to implement with SQ queries, are doomed for these problems. So in particular, they did this successfully for the planted clique problem. And there's been then since many works that are trying to show the statistical query lower bounds for some computational problems for which we don't have any efficient algorithms. Good, so just to review, the goal here is for lower bounds, we want to say some statement saying that unless the particular error that we want in the statistical queries is very small, then any statistical query algorithm has to make many, many queries. So this like super polynomial many queries. And for upper bounds, if we do manage to get an SQ upper bound, then this is very useful because it gives us a very nice abstraction for how to implement these algorithms, and then we can use them in like various models, or these are robust to noise sometimes. So okay, good. So this will be the setup. And the problem that we'll focus on is just the very basic problem of mean estimation. So the idea is that we'll fix a particular norm space. This will be X, so some norm space over RD, and some epsilon greater than 0, and now we'll get access to a distribution D, which is supported on the unit ball of the norm space. So on high-dimensional vectors whose norm in X is at most 1. And now we want to output an estimation to the mean. So this is a vector mu hat, such that the norm in X between mu hat and the mean of the distribution is at most epsilon. Okay? And we want to do this with statistical queries. Good, so in this paper by Feldman, Guzman, and Vimpala, who first studied this problem, they showed some SQ algorithms as well as lower bounds for doing this when the underlying norm space are the LP norms. And what they showed is that for P being greater than 2, they have an SQ algorithm which makes d log D queries, and the accuracy is like epsilon over log D. But then for P between 1 and 2, they very interestingly showed that there's an upper bound, but you need to have this epsilon over d to the 1 over p minus 1/2. And in addition, they showed that in some sense, if your algorithms are making the accuracy parameter, which is bigger than this epsilon over like this parameter in d factor, then you need exponentially many queries. So this is basically saying that you can't improve much on their upper bound, and you need this polynomial loss in the dimension for the accuracy. Okay, so the question is, what is it about particular norm space that basically needs the accuracy to be polynomial in the dimension? So when do we have this? In this case, for p being greater than 2, we were able to only achieve, they were able to achieve like just a logarithmic loss. Okay, great. So for this talk, when I'll say that when I can design algorithms to be polylogarithmic indeed, this particular accuracy, I'll call these norms tractable. So the main result in Feldman, Guzman, and Vempala can be stated as saying that all the LP norms are tractable if and only if p is greater than 2. Okay, so our result is some generalizations as well as other lower bounds in this line. And our first result is that for any symmetric norm, these are tractable if and only if the type 2 constant is polylogarithmic in D. And if you don't know what the type 2 constant is, this it's just a specific parameter that you can associate with a norm space. Basically measures to what extent the random sums of particular vectors grow with respect to the corresponding norms of the vector. So it's just some parameter of a norm space. And so these results are in line with the results in the LP norm. So, okay, sorry. So a norm is symmetric if it's invariant under permutation of the coordinates as well as sign flips. But more generally, we showed that this characterization doesn't hold for more general norms, and in particular, we show that for the Shannon P norms, so these are the norms over matrices where we measure the LP norms of the corresponding singular values, that these are tractable if and only if p equals 2. So this is like a different particular lower bound. Okay, so that's up top. So just the statistical query model. No, these are unconditional lower bounds. This is why it's meaningful.
Oh, I see.
Yeah, so you don't know, yeah, it's unconditional. Yeah. Yeah, so we showed it in the worst case. So if all your queries have error which is greater than some value, then you need many queries. Yeah, so we were playing around with some ideas, but okay, so in this case, Shannon P norms that show that like type is not really the answer, because Shannon P norms, they're the same as the LP norms in terms of the type constants. But yeah, so I don't know.